What happens when an interviewer wants to truly test your algorithmic efficiency? Merge K-sorted lists is a pattern mastery 100 heavyweight and a frequent guest at Google, Amazon, and Microsoft interviews. Over 40% of candidates get slowed down by the complexity and pointer management. Master this, and you'll prove you can handle multi-list merges, priority queues, and advanced patterns. Let's attack Merge K-sorted lists with the basic problem-solving framework, a stepwise guide for turning chaos into clarity, even in the toughest coding rounds. Let's break it down. Given an array of K-linked lists, each sorted in ascending order, merge them all into one sorted linked list and return its head. Example: input 145, 134, 26. Output 1, 1, 2, 3, 4, 4, 5, 6. Real-world example: think about a system that needs to combine multiple log files, each sorted by timestamp, into a single unified log for analysis. A classic interview extension. How would you merge sorted streams from different servers in real time? Let's assess it. What's tricky here? Naive approach. Merge the lists one by one using the two-list merge logic, O-kilonewton, time, where n is total nodes, works, but not optimal. Optimal approach. Use a min heap, priority queue, to always pick the smallest head among the k-lists, giving you O(n) log k time. Let's think step by step. Push the first node of each list into a min heap, keyed by node value. Repeatedly pop the smallest node from the heap, attach it to the merged list, and if there's a next node in that list, push it into the heap. Continue until the heap is empty. Let's dig deeper. Why a heap? It guarantees that at each step, you can efficiently, in O log k, get the smallest remaining node across all lists. Using a dummy node for the result list keeps the code clean and bug-free. Edge cases? Some lists may be empty. All lists empty? Output should be null. Here's the structure. Create a dummy head for the result list and a current pointer. Initialize a min heap and insert the first node of each list if not null. While the heap isn't empty, pop the node with the smallest value. Attach it to the current pointer. If the pop node has a next, push that next node into the heap. Move current forward. Return dummy.next. The time complexity of this algorithm is O(n) log k. Here, n is the total number of nodes across all lists, and k is the number of lists. Now, let's look at the idea behind this solution. We are merging k-sorted lists using a min heap, also called a priority queue. We keep a heap to always pick the smallest node among the current heads of all k-lists. We append the smallest node to the merged list, and if it has a next node, we push that into the heap. We repeat this process until all nodes are merged. Think of it like having k streams of sorted numbers, and always picking the smallest available number to form one big sorted stream. First, we check if there are no lists. If the input is empty, we simply return null. Next, we create a min heap that always keeps the node with the smallest value at the top. We use this heap to pick the next smallest node efficiently. For each linked list, we add its head to the heap, ignoring any empty lists. We then create a dummy node to simplify building the merged list. We also set a tail pointer that always points to the last node in our merged list. Now, as long as the heap has nodes, we keep processing. We take the smallest node from the heap. This is the next node to add to our merged list. We attach this node to the merged list and move the tail pointer forward. If the node we just added has a next node, we push it into the heap. This keeps the heap updated with the next smallest candidates. Finally, we return the merged list starting after the dummy node. So, to summarize, this algorithm first initializes a heap with all list heads. Then it repeatedly picks the smallest node and pushes its next node to the heap. This way, we build the merged list efficiently, even for multiple lists. It is elegant, fast, and simple. Now let's solve solution 1, merging k-sorted linked lists using a min heap. We'll see how to efficiently pick the smallest node among multiple lists using a heap. Step by step, we'll understand how the heap helps us maintain order. Time complexity is O(n) log k, where n is the total number of nodes across all lists, and k is the number of lists. Each node is pushed and popped from the heap once, which takes log k per operation. The idea: use a min heap to always know which list has the smallest current node. Push the head of each list. The time complexity of this algorithm is O(n) log k. Here, n is the total number of nodes across all lists, and k is the number of lists. Now, let's look at the idea behind this solution. We are merging k-sorted lists using a divide-and-conquer approach. We pair up lists and merge them, reducing the total number of lists by half in each round. We repeat this process until only one list remains. Think of it like a tournament bracket. In each round, lists compete 2 by 2, and the winner, the merged list, moves on to the next round. First, we check if the input has no lists. If it's empty, we just return null. Next, we set up an interval to control which lists we merge, starting with 1. N is the total number of lists. As long as the interval is smaller than the number of lists, we keep merging pairs. We go through the lists in steps of interval times 2. Each list is merged with its partner interval away, and the result is stored back in the first list of the pair. After finishing one round, we double the interval for the next round, so we merge the next bigger pairs. After all rounds are complete, the first list now contains all merged nodes. We return it. This algorithm uses a helper function to merge two sorted lists, just like our earlier merge two list solution. It uses a dummy node and moves a tail pointer to build the merged list. So, to summarize, this algorithm first sets up the lists and interval. Then it repeatedly merges pairs of lists in a divide and conquer fashion until all lists are combined. It is efficient, simple, and elegant. Each merge touches all nodes in the two lists, which costs O(n) per level. There are log k levels, giving a total time complexity of O(n) log k. This method works especially well when merging many lists, compared to naive sequential merging. Let's test our function to merge multiple sorted linked lists. With 1, 4, 5, 1, 3, 4, and 2, 6, it merges two lists at a time until all lists combine into 1, 1, 2, 3, 4, 4, 5, 6. For empty input, it returns. This approach efficiently merges multiple lists, keeps order, and works reliably for any input. Breakdown recap. We're given an array of k-sorted linked lists and need to merge them all into one fully sorted linked list. Conceptually, it's about combining multiple sorted sequences into a single unified list. Assess recap. A naive approach would merge the lists one by one using two-list logic, but that's slow. The optimal approach leverages a min-heap, priority queue, to always select the smallest node across all lists. This reduces the complexity significantly and makes it efficient even for many lists. Structure recap. Here's the plan. Create a dummy head for the merged list and a current pointer. Initialize a min-heap and push the first node of each list, if not null. While the heap isn't empty, pop the smallest node, attach it to the merged list, and if that node has a next, push it into the heap. Move the current pointer forward and continue. At the end, return the merged list. Implement recap. We implemented this using a min-heap, storing tuples of node value, node, to ensure proper ordering. Running it on LeetCode, the solution executed cleanly and efficiently merged all lists without errors. Check recap. We verified the logic across all general cases and edge cases. The solution runs in O(n) log k, time with OK space for the heap and produces correct results consistently. Closing insight. The key takeaway? When merging multiple sorted sequences, a min-heap is the most effective tool. It lets you efficiently track and select the smallest current element, keeping the process clean, fast, and scalable for any number of lists.